Hello, everyone, and welcome to today's webinar. I'm Jamie Funnell, a longevity actuary at Pension Insurance Corporation and current chair of the CMI Annuities Committee. And I'll shortly be handing over to Professor Andrew Cairns and Dr. Torsten Kleinow of Heriot-Watt University to take you through their work. I suspect they need little further introduction to most of you, but if you would like to know more, you can go to the IFOA website. Today's session will explore their work on a new longevity index for England. They will take you on a journey through its development and how it provides more granular insight into mortality inequalities across England than some other widespread methods. To help bring the index to life, as it were, and to help the actuarial profession keep up with the ever-changing technological landscape, they've even developed an app to support its use. You will all have the chance to register to test out the app and provide your feedback, and more information on this will be circulated after the webinar. Their work has been enabled by the Actuarial Research Centre, which supports actuarial researchers around the world to deliver cutting-edge research addressing some of the most significant challenges in actuarial science. So a few housekeeping points before I hand over. The presentation will last around 45 minutes with 10 minutes allocated for questions and answers at the end. You can submit your questions as we go along using the Zoom Q&A functionality, and we will do our best to address as many of these as possible. Any questions that remain unanswered will be collated into a single document and answered and posted on the ARC webinar series webpage. You cannot be seen or heard, so feel free to put the kettle on as necessary, and the chat function is also disabled for the duration of the session. The webinar is being recorded, so you will have a chance to catch up on anything you miss. And finally, as a reminder to those of you that require CPD, this can be logged for the event in the usual way. So without further ado, I'll hand over to Professor Andrew Cairns to take us through the Life Index.
Okay, well, thank you very much for that introduction. Without further ado, I'll move on to the next slide, just to acknowledge, as you've already mentioned, that this is part of a much bigger project funded by the Actuarial Research Centre of the IFOA, and also the Society of Actuaries and the Canadian Institute of Actuaries. And then a lot of the work, although it's Torsten and myself presenting today, a lot of the work, particularly the app that we'll talk about at the end, that has been done by our PhD student, Jo Wen, who was funded by the ARC on a PhD scholarship. So the outline for the presentation, we'll have a little bit of an introduction and motivation and background. So why are we wanting to develop a new index as well as the app? We'll talk about the data and the predictive variables that we use to predict high or low mortality. And then what are our objectives in terms of setting up, developing a new life index. Torsten will then take over to discuss a little bit more detail for a few minutes on the construction of the index, and then we'll have some results and then a demonstration of the app. So in terms of background motivation, what we know for sure is that mortality varies significantly between different subpopulations. So wealthy people tend to live longer, they have lower mortality. But then beyond that, the question is, well, how much variation is there, particularly when you're looking at groups of people rather than individuals who may have individually particular health conditions, but at the group level, be it a portfolio or a neighbourhood within England. So what is the best way to subdivide the population? And then we're thinking about, in asking some of these questions, we're interested in these sorts of applications. So in an actuarial context, setting base tables, but then also thinking about mortality improvement rates, because we've seen that in the past 20 years or so, that improvement rates have been really quite different in some of these subpopulations, typically faster improvements in mortality for the wealthier populations who already have lower mortality. And then thirdly, we want to also contribute to the wider debate on mortality inequalities. Now, in recent years, a lot of focus when we're looking at national data, a lot of focus when it comes to mortality differentials and inequality, a lot of that has been focused around the index of multiple deprivation, or IMD. So in particular, the IMD splits the population up into neighborhoods that have similar levels of deprivation and into these deciles. And these deciles do give a reasonable prediction of mortality, in the sense that the most deprived group has high mortality and the least deprived group has low mortality. But the IMD is designed for a very wide range of purposes, and it was certainly not optimized, or even perhaps they didn't even think about mortality when they were designing the index. So the question is, can we develop a better, a customized mortality predictor? Now, on this and the next slide, I'll go over a sort of known problem in terms of where the pitfalls are in terms of using the IMD. And the starting point is to construct what you might describe as a standard table for each of the 10 deciles. So here's our sort of traditional actuarial MX, but the MX is now dependent on the particular deprivation decile that you're looking at. So it's for a particular year, T and age A, this MDTA is the actual deaths in decile D divided by the exposures in that decile. Mathematically, it's written down in this sort of way, and this will just now and then a little bit later, we'll give a bit more detail about what's going on here. But the key point is that we're counting only deaths that are in particular neighborhoods, what are called lower layer super output areas, or LSOAs. We're only counting LSOAs that are in that particular decile. So we need to just, for you to explain what is an LSOA, and then what are the death counts and the exposures counts. So how are they calculated? We need to think about, first of all, what is an LSOA, because this is key to the life index. So an LSOA is a small neighborhood, and there are just under 33,000 of these across England, with an average population of around about 1,600. And within each neighborhood, these are socially homogeneous, or that's the intention. So, and the boundary of the neighborhood gets drawn in a way to ensure this. And the key thing also is that a wide variety of data are available at that LSOA level. So that's in terms of deaths and exposures, which we need to calculate death rates. But then also, very importantly, there's quite a wide range of socioeconomic variables that Torsten will talk about later, which are used to predict high or low mortality. So notationally, DITA is the deaths, and it's specific to LSOA I, and year T and age A. So within the data that we have, most of these death counts are going to be actually zeros or ones, because there are not that many people at each age within the LSOA. And then the exposures, again, single ages across the LSOA. And then that's what we've used to calculate this decile specific M hat. So we're adding up over all of the LSOAs within that decile. So now what we're going to do is to compare actual versus expected deaths for subgroups within each decile. And this chart is showing the urban and rural subdivisions within each of the deciles. So on the x-axis, we've got decile 1, which is the most deprived on the left, all the way through to decile 10 with the least deprived. And if I pick out decile 4 in particular, what we're seeing here in terms of these charts is that within that decile, if we just looked at the very rural areas within that decile, then their mortality is around about 80% of what was expected in terms of the numbers of deaths. And that's within this particular age group, 70 to 79. And in contrast, for the black curve, which is the conurbations excluding London, the conurbations excluding London tend to have higher mortality than would be predicted using the average for that particular decile. And it's a similar picture across all of the deciles, but it's a narrowing gap, particularly on the right-hand end, narrowing also at the left-hand end, and a big gap, big differences between the urban and rural areas in the middle. And it's a similar pattern at other ages for both males and females. And then also when we look at regions rather than urban and rural, we've got the red and the black by decile for the northeast and the northwest of England. So they're slightly higher mortality, but not quite as big a gap as the urban and rural. But it's also a slightly different pattern. It's more consistent across all deciles, this regional effect. So moving forwards then from the IMD, our objectives in developing a more the life index is to publish a robust and reliable mortality index at the neighborhood or LSOA level that is open access to explain as much as possible of the variation that we see at the LSOA level in mortality using publicly available data. And then that publicly available data is going to be socioeconomic predictive variables, care home populations based on census data, and then urban and rural class, which is what we identified particularly. And then to minimize, as a consequence, unexplained urban, rural, and also regional differences. And then going beyond that, what we're trying to do is to provide an open access toolkit for actuaries just generally, and for mortality specialists to provide a tool and a benchmark that they can use in their own work using rating and valuation models. And then lastly, to facilitate some debate and action on how to tackle mortality inequality. So I'll now hand over to Torsten just to give a bit more detail in terms of the construction of the index.
Yeah, thank you, Andrew. Let me just quickly share my screen. So what we now want to talk about is the construction of the life index, which is of course the basis for the apps that we will see later. And as Andrew already mentioned, the observations that we have for each of those LSOAs is the death counts and the exposures, of course, but we also have a number of predictive variables which we observe for each LSOA. And those are mainly socioeconomic variables, but also some others, and we will go into details later. So to construct the index, we start off with constructing what we call the relative mortality risk. We define a baseline, which is the mortality rate for the whole of England, by just taking, well, the total deaths in England and divide them by the total exposures in England. So in formulas here, you would take the death counts for LSOAs and sum them all up, and take the exposures for individual LSOAs and sum them all up. And this ratio, of course, gives us a mortality rate for England as a whole. So if we had no further information about an individual LSOA, we would expect that we observe this number of deaths here in an individual LSOA, where we take the exposure in that LSOA at a certain year, at a certain age, multiply it with the mortality rate for England, and sum over all the ages and years, and we would end up with a expected number of deaths that we would see if all LSOAs would have the same mortality rate, which is just this baseline mortality. Now, we know that there are differences between LSOAs in terms of mortality. So what we are looking at is the actual observed number of deaths that we have in an LSOA over a certain range of years and ages, and divided by the expected number of deaths. So if this ratio is greater than 1, then we have a higher mortality rate in LSOA-I than what we would expect, assuming our baseline mortality. And if it is lower than 1, then mortality in that LSOA is lower than what we would see in the whole of England. So this relative risk will be the basis for our life index. And what we now want to do is try to explain this relative risk using some socioeconomic variables and some others. So here are the variables that we want to use. There are 12, and we tried many more, but we ended up with those 12 being, in a sense, the best to explain mortality. And as you can see, the first 9 are all kind of socioeconomic. They're related to employment, to education, and income. Then we have the variables 10 and 11 at the bottom here, and they are particularly important for us, and we will come back to those because these two describe the proportion of a population that lives in a care home in an LSOA. And of course, if we compare two LSOAs, which are pretty equal, but one has a care home and the other one doesn't have a care home, then of course we would expect a higher mortality where there is a care home, just because of the fact that people move into the care home, maybe from neighboring LSOAs, move into that one, into the care home, and then increase mortality. So we will have to correct for that when we construct the index, and we will come back to those two variables. The last one, urban-rural classification, where it's not really a socioeconomic variable, but describes, of course, this LSOA and what kind of setting it is. We have 5 classes that we want to consider there. So these are urban conurbations down to rural hamlets and isolated buildings. And we have then decided that actually the mortality in London is so very different from the mortality in other parts of England that we have split the urban conurbation class into London and others. Yeah, so we end up with those 5 classifications for urban-rural, that is for this urban-rural classification. So how do we construct now the index? Well, as I said, we want to explain the relative mortality risk using those socioeconomic variables that we have just seen, those 12. And that, of course, is a typical regression problem. We are interested in the conditional expectation, as a statistician would say, of the relative risk, the relative mortality risk, given a certain realization of the predictive variables. So this conditional expectation here is a regression function. It's a function of x. And the statistical problem is now to estimate that function x. That's our first step, or our next step. So there are many ways to deal with a regression problem. And we have chosen here a random forest estimator. So this is a estimator which could be described as a supervised machine learning algorithm, or you could just describe it as a non-parametric statistical estimator for this regression problem. But of course, there are others that could be used, and we've done some, in some previous research, we used a local linear regression estimator, but here it's a random forest estimator. So what I now would like to do is talk a bit about the random forest method, without going into too much detail, but just to give you an idea of what we actually did to come up with the estimator for F. And then we will use that estimator for F to construct the life index. So for the random forest estimator, what we do is we divide our training sets, we divide our set of LSOAs, so these 32,000 LSOAs, into 2 sets, a training set and a validation set. And we will fit our estimator 2 observations in the training set. Now, a random forest, as the name suggests, consists of a large number of trees. And in this case, those are decision trees. So what do we do to construct a single decision tree? Well, we first choose a random subset of LSOAs from the training set. So we've divided our total number of LSOAs into training set and validation set. And now we choose a relatively small number, maybe say 5,000 or so LSOAs from the training set. And we fit a decision tree to only those 5,000. So we fit this decision tree only to that subset. And there's a little kind of technical detail here in the third step, which we have to think about, but that's just a technical detail. So let's ignore that for the moment. But that gives us then one fitted decision tree. And then we do the same thing again. So we choose another random subset and fit another tree and so on and so on. And in that way, we get loads of trees. And that gives us a forest. And then we average over the trees to get our final estimate. So the question is now, how do we fit, to drill down a bit deeper here. So how do we fit an individual tree? And that I want to show in an example rather than in all generality. Here's a typical example where we have reduced the number of predictive variables from 12 to 2, just so that we can plot actually something on the slide here. And the 2 variables I have chosen is the old age income deprivation and the employment deprivation, because those 2 turn out to be the most significant actually to explain mortality. So what we have in the plot here are some gray dots and some red dots. Now the gray dots are all LSOAs, so 16,000 or so in the training set. And from that, we have chosen a random subset of red dots here. And those are the 5,000 LSOAs that we use here to fit our decision tree. Now, for each of those dots, we have an income old deprivation index, and this is all normalized here to be on a certain range of values. And we have an employment deprivation index here on the y-axis. And then, of course, each of those dots also has attached a relative mortality risk. So what we now want to do is use those 2 variables here to explain the relative mortality risk. And the way that a decision tree does that is it splits the LSOAs that we have here, the red dots, the ones that we use for fitting this tree, into different subsets by just putting rectangles into this plane here, into this R2 plane. And what the algorithm does is it first looks into the 2 dimensions and decides which one to split. And in our example here, the algorithm decides to split along the income old dimension here, so the old age income dimension. So it would put a line here and would decide that all the LSOAs which are on the left of this line, so all of those ones here, have a certain level of mortality, a relatively low level of mortality, because those are kind of the least deprived here. And then we have the LSOAs on the right side here, which have a relatively high level of mortality. The algorithm would then continue to decide whether there should be more splits. And in our case here, in our example, the algorithm has decided there should be another split here. So we now have 3 sets of LSOAs, and each of those sets would have a different level of mortality, but all LSOAs within one set have the same level. So what we get here is a kind of piecewise constant function over a 2-dimensional plane. That's what a mathematician would maybe call that. And then we continue. Yeah, so we have more splits here. The algorithm decides where to split. So the 3rd split also in the old age income dimension. And then the 4th split appears actually here. So it's just this band here of LSOAs that we had before is now split into 2 along this line. So we have a set of LSOAs sitting here and a set of LSOAs sitting here, and they would be distinct in terms of mortality. So we continue with the same idea, and in this case here we stop the algorithm after 6 splits. So we have now 6 sets of LSOAs. Each of those sets has its own level of relative mortality risk. The ones here on the left, for example, all the LSOAs which are here in this area, so on the left of the S2 split, they would all have a relative risk of 0.7. Then all the LSOAs in here have a certain relative risk, all in here, and then the ones up here, those are the most deprived LSOAs. They have the highest relative mortality risk, as we would expect. So that gives us one tree. That's just one decision tree. And now we would choose a different random set of say 5,000 LSOAs, and we would fit a tree again, and that would look very similar to this one, but it wouldn't be the same. And then we fit another one and fit another one and fit another one. And in the end, we take all those trees and we average over them. So if we have a total of B, capital B trees here, we just take the average over all of those to get the final value of our estimator, or random forest estimator here, for a certain point in this, and for a certain value of all the predictive variables. Now, that regression estimator here, this conditional expectation of the relative risk given the predictive variables, that of course cannot be the mortality index. It is a smoothed version of the relative risk, but we shall not forget that we have some LSOAs which have an artificially high mortality because we have care homes in those LSOAs. The vast majority of LSOAs doesn't have care homes. So we somehow need to correct for the care homes. And we do that when we construct our index. So when we define our longevity, a longevity index for England here, then we use this function f, or the estimated versions that we have just found with the random forest estimator. But we are not applying it to the characteristics that we have observed for the LSOA. We are applying it to kind of modified characteristics. And the modification only happens here in those two variables, x10 and x11, which describe the proportion of the population living in care homes. So these are adjusted. And they are actually, in all LSOAs, we replace those with their average values over the whole of England. So we take the average proportion of people living in care homes, and here also the average proportion of people living in care homes with nursing. The difference between the two is just nursing, no nursing here and nursing here, and replace them with that. And that gives us modified characteristic, socioeconomic characteristic for the LSOA. We apply our function f, or the estimated value, or the estimated function f, to that, and that gives us the index. So to summarize this idea, so there are three steps in a sense involved in constructing the index. The first one is to define the relative risk by just taking the actual observed deaths in an LSOA and divide by the expected number of deaths that we would see in this LSOA if there was perfect equality between all LSOAs. Then we have this relative risk. We then explain it using some predictive variables. Those are the 12 variables that we talked about earlier. And we want to estimate this function, which explains the expected relative risk given the predictive variables. And then we construct the life index by replacing only the care home proportions in our predictive variables, and then apply this estimated version of the function f, of our regression function, to that modified predictive variable vector. Now, I have said earlier that the relative risk does not depend on years or on ages or on sex or whatever, because we sum here over all years and we sum here over all ages. But of course, the estimated version of the life index, and that's all we can report, we can only estimate this thing, then it does depend, of course, on the data that we use for the estimation. So the index that we will report in the app does depend on whether we use mortality data for males or for females, and what age range we use to fit the function f, and what calendar years we use for the fit, and which ages and years we use here when we sum up over all the tests. So in the version that we will show in the app, the index will depend on sex, and it will depend on age. The years will always be fixed. We always use the years from 2001 to 2018. So that's the mortality experience that we use. The age range that we use will be a 10-year age range centered around the age of interest. So if we want to know the index for age 75, we use ages from 70 to 79, for example. So with that, I will hand over to Andrew again, who will show you some of the empirical results, and then also show you the app itself.
Thank you. So let me just get back to full screen. So the results, we'll just talk about the distribution of the index values to show what sort of range we get there, and also to look at life expectancies. I'll briefly talk about regional variation because we had talked about that previously, and then compare the IMD versus the life index to highlight the differences. And then I'll get on to the demonstration of the app. So the first question is, well, how much inequality is revealed by the life index? So if we take females aged 65, so as Torsten said, the index is age specific and it's also sex specific. So at age 65, you can see that there are some LSOAs which have very low mortality, down to around about 0.5. So 50% of the national mortality for females at age 65. And then there's other LSOAs at the other end of the spectrum that have double the mortality of the national rate, females at age 65. And age 45, it's a similar sort of spread, maybe just slightly wider. But as with many populations, that we see a gradual narrowing of the inequality as we go to the higher ages, age 85 in this example. So that's the index. But of course, it's often much easier for people to interpret if we talk about life expectancies rather than these relative risks. So these charts here are centered on the median, but then have plus and minus 15% around that median, just to give you an idea of the percentage differences at different ages. And it's by a small margin, the widest at age 65. And you can see in terms of the x-axis that there really is quite a substantial variation from the shortest lived below 19 years and then above 24 years for the longest lived. And these histograms are covering all 33,000 of the LSOAs. If we look next at region, we can just comment that the new index does explain a lot of regional variation better than the index of multiple deprivation did. So we have three charts here. The first one is just the raw mortality by region. From northeast, northwest, and so on down to the southwest. So the northern regions have high mortality, southern regions have lower mortality. But as we all know, that there's quite a lot of variation, big differences between these regions in terms of the socioeconomic mix. So more deprivation in the north, and that is a cause of the high values here, or at least in part. So if we standardize using the age and deprivation standardized mortality in the right-hand two plots, we can see that the gap does narrow using deprivation as a measure. But if we then move to the life index, that gap between the different regions narrows quite a bit further. It doesn't narrow completely down to nothing, no gap, but it does narrow quite substantially. And particularly if you put London to one side for a moment, then the other regions all are quite narrow, whereas London does seem to be a bit of an outlier in terms of its rather faster improvements over the last 20 years or so. But the big north-south divide, when you actually look in detail at these different lines, that north-south divide is not quite so obvious as it was before. This slide and the next one compares the IMD versus the life index. So what we're doing here for males aged 75, I'm plotting, each dot is a single LSOA, and we're plotting the IMD percentile and on the x-axis and the life index percentile on the y-axis. And if there was really no difference between the IMD and the life index, then all of these points would lie close to the diagonal. And what I'm counting in this table here is the difference between, so if it goes from the 5th decile to the 7th decile, that would be a difference of 2. And what we can see here just in numbers terms is that there's only 12,000 LSOAs that have stayed in the same decile under the two ways of measuring mortality. And there are quite a decent number that have jump by 2 or more deciles. Now, this is the same plot but colored according to urban and rural characteristics. And so the main group of points that are off the diagonal are the very rural areas. So that the rural areas, and this is what we saw in the chart quite early on in the presentation, that the urban rural areas had much lower mortality than other types of urban rural area. So that's why all of these blue dots are there. There's also a little bit of a cluster of orange dots in London, and these dots are mainly in the Kensington and Chelsea area. Now, starting to think about the app, there's a choice to make in terms of version 1 or version 2. So version 1 is focused on the index as it was described by Torsten. So that's what we call R1 using the random forest methodology. And the M base is the average mortality for England at age A and also year T. And then there's a second version that you can choose from where there is an additional relatively small adjustment for the regional or rather even more local variation in mortality. So what we're doing is we are, in terms of this additional adjustment, R2, these are done at the level of clinical commissioning groups. And these are responsible for the planning and commissioning of healthcare services for their local area. And the local area might be a large city, or it might be a county, for example. Now, the variation in, as I've said, in R2, that's very much smaller than variation in R1, but it's not negligible. Now, if we think about the two in terms of how do we use them, then R1 is that's really about the debate at the national level in mortality inequality, whereas the R2, which is specific to each CCG, is really thinking about how do individual CCGs compare on a like-for-like basis. So looking at another CCG that has a similar mix of people socioeconomically. Now, in terms of the results, just picking out one or two areas or neighborhoods. So we've got some neighborhoods that have the lowest mortality that are mentioned here. And these are taken out of the top or bottom 20 LSOAs. And I picked out ones that are in the top or bottom 20 for both males and females. And of course, what you'll see here this is the R1, the socioeconomic part of the index, is that they're mainly in the south, whereas the areas that have the highest mortality, these are typically in the north. And that's really simply reflecting the underlying socioeconomic and urban rural differences between these areas, rather than anything that's to do with simply being in the north or the south. And then at the CCG level, so that this is the R2 additional factor, these are the CCGs, clinical commissioning groups, and these are rather more mixed in terms of who's at the top and who's at the bottom. Sheffield, for example, or Norfolk and Waveney. So that's what we're saying here, is that Norfolk and Waveney has lighter mortality than other CCGs with a similar socioeconomic and urban rural mix. And Sheffield, just as one example, Sheffield, to give you an idea of the order of magnitude, Sheffield has 8 to 9% lower mortality compared than the life index predicts. Portsmouth down here has around about 8 to 10% higher mortality than the basic index would predict. So I'll now move on to introduce the app, just one or two slides to start with, and then the demonstration. So the app has been developed to help non-expert users to explore the index and discover mortality inequalities between different areas. We have information by LSOA, so residential postcode in particular. I do stress the word residential there. That maps to the LSOA, or you can use a lookup table. But we also have maps by clinical commissioning group, or by region, or Westminster parliamentary constituency. And then there are various inputs that I'll talk about during the demo. And then the outputs will include the life index and also period remaining life expectancy. And then this graphic just gives an idea of how things link up. So the postcodes map you into an LSOA. And then, for example, the region mapping, and the averages there are deriving their index values using these LSOA values. And finally, just before we go on to the demonstration, just to manage your expectations. So the app that you will be able to access yourselves after the webinar, it is what I would describe as a beta version. So it's under development. So the numbers we're quite happy with that underpin it, but it's more just the look of the app and the explanations. So is it easy to use? Does it give you the information that you're looking for? So we are very happy to get your feedback. What do you like about the app, but also what might be improved? The app is hosted on a server that has limited capacity. So if there are lots of you on at the same time, it might get a little bit slow, but you can check how many users there are. And lastly, we are not professional software developers, so it's never going to be perfect. So I'll stop the slides, and then I will now move on to the show the app. So I'm now running this just on my laptop, just to avoid any further problems with the internet. But what you will see when you log on to the website will be just the same. So there are 3 tabs on the app. The first one is just a little bit of a description of what the app is about, and also some contact details if you want to give us feedback. And then there's the index by postcode, so that's really the LSOA detailed information, and then an interactive map. So if we start off with the index by postcode part, there's various bits of information. So there's a user guide, first of all, and then you can either search by postcode. So there's, I'll just choose this one, M28 2GF. And just as a reminder, when you're entering a postcode, it must be a residential postcode rather than a postcode that is limited to commercial businesses. But you can also search by typing in the name of a town, and then you'll have a drop-down list of LSOAs. But the names of the LSOAs are not very easy to negotiate. You then put in an age, so we'll just take 60. You then choose between males and females. Although, of course, the index for males and females is, these are quite highly correlated, but they are a bit different. And then lastly, we have to choose between the index type. So this is the socioeconomic only, or whether you have this additional adjustment that I referred to before, R2, which includes an adjustment for the clinical commissioning group. So you then click on show index, and a few seconds later, you get this information popping up. So there's the name of the LSOA. So this is where the postcode maps into this particular LSOA. It's in the Northwest region. We're looking at age 60. And then here's the index value, 0.61. So that's an area that has relatively low mortality compared to the national average. And then there's a decile and a percentile. And a high decile or a high percentile means low mortality. And then lastly, in the table, there's a life expectancy from that particular age 60 and for males. And then also on this page, there's a bar chart that helps you to see the chosen LSOA, so Salford 14A, relative to all of the other LSOAs for that gender and age group. Moving next to the map, interactive map. So there's some different choices to make here. So one is to choose between region, or plotting a map for a particular region or a CCG or a constituency. So we'll choose the Northwest, and I'll go for, say, age 55. And again, same choices as before, males or females, and then socioeconomic or with the additional regional adjustment. So we'll set that going, and that again comes up relatively quickly, provided there are not a lot of other users. So if there are many users, you're then in a queue. if there is a queue or many users, things are going slowly, you can click on this box here to find out how many people are. And if there are lots of users, you might want to come back later on. But here's the map for the northwest of England. And in terms of the color scheme, so there's a legend here. So the light yellow is for low mortality, and the darker reds at the other end of the spectrum are the high mortality. And of course, before we zoom in, you can see that most of the dark reds are centered around the big cities, Liverpool and Manchester, but there are also clusters of dark reds up the coast from Liverpool, which are centered around the various towns that are up that coast. So you can then move the map around, and you can then start to zoom in. And I'll try and move over towards Manchester. So you can now, as I move the mouse around, you can hopefully see that as I move the mouse around, there's a boundary which gets drawn around the LSOA. So each of these little blocks are the individual LSOAs. And I can then click on that LSOA, and a little box will pop up to tell you the name of the LSOA, and then it'll give you some of that information, the index value and the life expectancy. So that's an example where we have a low index and high life expectancy, so 29 years, 11 months, keep that in mind. And then if we go to another LSOA near the center of Manchester, dark red, 29 years becomes 22 years and 11 months. So there's a big drop in the life expectancy going from one LSOA to another. So that's the map. And then the last thing that's available to you down at the bottom left here is you can either have the interactive map, or you can click on this button to get a summary for the region. Northwest, age 55, index value 1.15. So that's telling me that the Northwest just generally has higher mortality because of socioeconomic factors compared to the national average, and then an average life expectancy. And then just to finish off with, we can maybe look at one example. So previously, when we were looking at CCGs, we picked out Sheffield, if I can find that. Oops. So Sheffield was doing well in terms of, on a like-for-like basis. And so from age 55, this is with socioeconomic relative risk only, 26 years and 9 months. But if we click and add in the CCG effect, that 26 years and 9 months goes up to 27 years and 4 months. So there's a noticeable difference in life expectancy on a like-for-like basis because you're in Sheffield rather than somewhere else. So I think with that, I will stop sharing, and Jamie, I'll hand back to you as chair.
Thanks very much, Andrew, and Torsten for that. Just thanks everyone else for coming back and dealing with the technical difficulties we had earlier. Apologies for that. We may run over by 5 minutes as a result. We have had a couple of questions in. Just keep them coming in the Q&A section now, would be great. So firstly, are houses within an LSOA truly homogeneous? Sort of many houses have, 1, 2 beds and luxury 5 beds. So is there really more variation than a true underlying socioeconomic group? That's the first.
Yes, so I think that's a fair and a good question to ask. It's certainly true for many estates in particular. I would maybe say that you will have this variation, and particularly now the sort of newer housing estates, you maybe do have to have a mixture of these big executive villas, but also some social housing within the same development. So you're quite right. But in terms of the data and the results that we're getting, that we do still, in spite of that, do see this very significant variation in terms of the predicted mortality and also the sort of quality of fits that we see when we look at the goodness of fit in the results. So you're quite right. So there may be some LSOAs where there is that heterogeneity rather. And so, you could maybe say that within an LSOA, there may be some further variation that we're not able to pick out. But of course, it's also the case that it's about how you understand what the index is telling you. And the index is telling you what is the average for this neighborhood. And if you look at the neighborhood and it does look fairly similar in terms of types of housing, you can say, well, it's going to apply across the whole of that. But then if you have a different type of neighborhood that has this sort of mix, then you would, if you wanted to, you could potentially make further adjustments, but that would be using different types of data. And that's maybe where the types of work that some actuaries use using geodemographic profiling, that's where it would be able to probably separate that sort of thing out. And so that's one of the differences between what we're doing using open access data sets compared to the what is available on the commercial market.
Great, thanks very much. So next question is, have the values of the predictors varied with time, and have you controlled for sort of movement in the LSOAs?
So again, that's a good question. So, and it's something that we've been looking at, and just as sort of one starter there, that when we had the chart by region, that you could see that London was drifting below the other regions. And so although the way we've calibrated the index in its current version, there is no time trend that is allowed for within that. But it is something that we're asking ourselves, well, how can we build that time trend in? And in part, it may start off by looking at with some of the predictive variables that are based on the index of multiple deprivation. So we have the IMD and the subdomains that are available on maybe 4 or 5 different time points over the whole of the calibration period that we're looking at. And so we can certainly look at that, and we will be looking at that to see how much variation there is, and indeed whether we can come up with a next version of the life index that is doing exactly that, what that questioner is asking. But we have certainly done some work on looking at different time periods, and there is some variation, some movement from one period to another. So the first 9 years and then the second 9 years. So there is some movement, but often it's more to do with the random variation that you have in the deaths and exposures, as well as 1 or 2 of the predictive variables. And then there's a few other LSOAs where there are maybe some slightly more substantial changes. And I think those are the ones that we want to focus on in terms of could we have predicted those movements by building some sort of time element in.
Yeah, great. So it sounds like there's lots of further work that can be done. Sort of more practical question. So just complimenting the app, saying it looks useful, but is there a way to sort of get a database with sort of all the index values for all LSOAs?
Okay, so yes is the answer to that. So it's really by contacting myself or Torsten. So we have, it could either be in a spreadsheet format or directly in R. So we're very happy to be able to provide that data set, because if you, for example, have a long list of postcodes that you want to get an index value for each one of those postcodes, then you do not want to laboriously go through them one by one on the app. So you just want to be able to take the data set. So yeah, so the answer is that we're very happy to provide that. And then also as an additional option that the app itself is just a bit of R code and some associated data sets, and that can be provided as a zip file, so that you could, provided you're an RStudio user, so that's the key thing. If you're an RStudio user, then you could run the app on your own laptop rather than accessing the website. But of course, it still doesn't solve the problem of having to type in postcodes one by one. So the app is more just to explore what's going on across the country in some sort of more general type of way.
Yeah.
Or indeed where you live.
Yeah, I'm sure everyone will be putting in their own postcode to test it out. But yeah, back to a more technical question, I think. Why calibrate to 10 years around age, and how sensitive is the index to this choice?
Torsten, you want to have a go at that one?
Yeah, of course. Yeah. Well, we have chosen to use 10-year groups. We started off with actually looking at kind of 60 to 69, 70 to 79, and just fix those groups. And but that didn't turn out to be very very smooth. And then have decided to just use 10 years, kind of 5 to the left, 5 to the right of whatever age the user is interested in. But there's no specific reason to choosing 10 years. And we haven't done much in terms of investigating how sensitive the results are. But what we find is that they are quite smooth, and that's was for us the main point. But of course, we could try others. I mean, the methodology is, of course, general, and we could use other age ranges. We could also restrict the number of years that we use, or even restrict the LSOAs or sorry, not the LSOAs, but the death data and the exposure data in some other way. That would be possible, yeah.
But I would just add to that in terms of 10 years versus 1 year or 20 years, I mean, the 10 years is partly to handle sampling variation in the data. So if you just had 1 year of age, then we'd have a lot fewer deaths, and so there's more noise in the data.
Yeah, makes sense. Could this ever be expanded to consider healthy life expectancy, and would this show further inequality across the country?
Again, a very interesting question. I think it's not something I've not really particularly thought about, so I'm thinking on the hoof here, but the slight challenge, I think, is probably in terms of what exactly is the definition of healthy life expectancy, and how is that measured? And you know, whereas with deaths and, well, particularly deaths, that's a very precise or well-defined event, shall we say. The exposures themselves are always estimates anyway, so there's a bit of uncertainty around that. But the defining the end of the healthy part of your life is something that's slightly more uncertain. So it'd be nice to be able to try and do that, but it's maybe you know, something that would maybe require a lot more thought, and it might even sort of being at a sort of different level of detail in terms of LSOA or something, or CCGs or something like that. It's definitely worth thinking about. We'd have to think about the data.
Yeah, it sounds like the extra work is mounting. But the next two questions are very similar, with one of them being phrased a little bit negatively, I would say. But a big drawback with life is the E, that it's for England only. And is there any prospect of a UK-wide index, or equally for other countries?
Mm-hmm. So the E versus S, W, and NI, which of course would muck up the nice name that we've got for the, but mucking up the name is not a good reason for restricting to England. So yes, it is very much on our agenda to extend to the other countries within the United Kingdom. Wales should be relatively straightforward, because it's coming from data from the Office for National Statistics, where we know what the data is there, although we just have to be careful that the predictive variables are defined in the same way. Scotland and Northern Ireland will require a lot more effort and resources. So you know, we do need money to, you know, be able to devote some of our time to construction of these indices, but we really would like to be able to do that in order to give full coverage of the whole of the United Kingdom, because I do think that would make it more likely to be usable by actuaries who have portfolios that cover the whole of the country. And then looking at other countries outside of the UK, we certainly haven't done anything with other countries, but what we have done is to just sort of think about what are the criteria, what do you need to do, what type of data do you need, for other countries. So, and one of the questions there is, what sort of neighborhood or geographical area are you able to get good data for? So I've certainly seen some work for the United States relatively recently, where they've done it at the county level, which of course are much larger than the LSOAs that we have. But it is at the county level where they have the population and deaths data, and then they also have the socioeconomic variables as well to go with that. But it's much more challenging in the US to get the same smaller area detail. So that's the type of question. And then a rather different type of index would be one that's actually accessing administrative data at the level of individuals. And that might be using income tax returns or things of that sort. And I certainly have seen things of that sort in the United States in particular, but also I've done some work in using Danish data, but it's a relatively small population. So you can do things with different data sets, but but there is this choice between geographical or individual information with obviously more restricted access to those records.
Yeah, it certainly seems to be ability to access that data that is one of the main issues there. I think we'll just take one more question before wrapping this up. Slightly different slant on this one, but have you considered how this data can be used to inform government policy and target actions of most benefit to particular areas?
Yeah, that's a very interesting question. So one of the things we're hoping to do with the app is to use that as a way to talk, or as an opening to talk to health people in the health area and in government or the National Health Service. And it's partly why you will see in the app that we have the clinical commissioning groups and the parliamentary constituencies, so that if we do talk to different groups, then we have something that is specific to their particular needs. So that's in terms of the main life index. But then what we're also doing is we're looking at cause of death data, because what we would like to know is within a particular area, well, what are the big causes of death? So, for example, in that table of CCGs, why is Sheffield below its benchmark? So what are they doing right? So is it the population that are leading healthy lives, or is it the actual healthcare that's better than other cities? So that sort of thing. So it's definitely on our agenda to go out there and to try to talk to the health professionals.
Great, thanks very much, and apologies to all the questions that we haven't got around to answering. There are several more, and they have been noted, and we'll look to answer those after the session. So it just leaves me to thank Professor Andrew Cairns and Dr. Torsten Kleinow again for taking time today to present to us, and everyone for attending. There are several more upcoming webinars in this series. So there's one on the 30th September on cancer morbidity risk modelling, and another on cause of death data on the 21st of October. So do look out for those. And finally, just a reminder that you can email to get access to the Life app, and please provide feedback on that. And there will be a feedback survey once this closes down, and a link will be emailed round as well. So please do take a minute to fill that in if possible. And thanks everyone, and have a great rest of the day.